So friends, after looking at the real life example, now we will go back to our OSI model and try to understand it in detail technically. So these are the 7 layers. And as you can see, I have shown top 3 layers in green, the bottom 3 in black, and the transport layer it is in red. So the top 3 layers are the software layer, while the bottom 3 is the hardware layer. While transport layer is the heart of OSI, which is the interface between software and hardware layers. Now we will understand what each layer does, what protocol it deals with, what are its PDUs, which is protocol data unit, and what devices are responsible for each layers. So our story starts with the application layer, where the user interacts. So you open your browser and type in URL https google.com. The browser prepares an HTTP GET request, the client asking the web server, hey, send me the homepage of google.com. Protocols like HTTP, DNS, FTP, SMTP, and SSH live here. It's where the requests are formatted and passed down. Importantly, no actual data transfer happens here. Instead, the layer constructs the intent, what the user wants to do. This is where the API, cookies, headers, and user authentication tokens are handled. Now we move to the presentation layer. It prepares the application data for transmission. The GET request is encrypted using TLS. That's padlock in your browser. So the HTTP request becomes ciphertext, unreadable to anyone intercepting it. Think of this layer as a translator, making sure the format is correct and secure for transport. It also handles compression and encoding. Now with the data encrypted, we now need to manage the connection. That's the job of session layer. Here your system manages a session with the server, starting with the TLS handshake, which sets the cryptographic parameters. Think of this as two systems shaking hands, agreeing on rules before talking securely. It facilitates authentication and authorization by coordinating or triggering them when a session is initiated. For example, during a remote desktop session, a session layer ensures that the login credentials are exchanged properly before the session is established. Once the communication is over, the session is terminated. Because of this layer, you can have 2 tabs in your browser, one checking your Gmail and other having YouTube playing. Protocols like SMB, RPC, and NetVoice rely on this layer to manage persistent connection, essentially important in file sharing or remote desktop sessions. So in all these 3 layers, the PDU is data, and the devices which are responsible for all these three layers is the end user devices. The function of application layer is the end user interface. Here the end user intent is recorded. In presentation, the data is encrypted, decrypted, and compressed, while in session layer is responsible for managing sessions, like establishing and termination of sessions. These are the protocols in each layer. In application, we have HTTPS, HTTP, SMTP, DNS, SNMP, and Telnet. While in presentation, we have TLS, SSL, JPEG, and MPEG. And in session layer, it's RPC, NetVoice, and SMB. Now, at the transport layer, each encrypted message is chopped into segments. So what are segments? So until above 3 layers, it was pure data, and now from this transport layer, it starts converting into PDUs. It is in this layer we ensure perfect delivery of the message. This is where TCP kicks in. It ensures reliable delivery through sequencing, acknowledgement, and retransmission. A TCP handshake, which is SYN, SYNAC, and ACK, is performed here, creating a virtual circuit between your browser and the web browser. Each segment gets its source and destination port. So when you are accessing any website, then source is a randomly high numbered port, say 49512, and destination is 443, which is for HTTPS. So there is additional header in front, which is the port details. So without this layer, you have no way of knowing if the data is arrived or in what order. So in this layer, apart from data which comes from the above 3 layer, there are 2 things which gets added. One is the source port, another is destination port. So these are the 2 headers which gets added. Here there is one more protocol, UDP, which is used when we need speed and delivery is not important. Example, for voice and video transmission. When you are watching any web series in Netflix or streaming movie in real time, that is where UDP transmission comes into picture, where delay is important rather than quality. So how is TCP and UDP different from each other? So TCP uses 3-way handshake, while UDP just sends a message and does not wait for the acknowledgement. At the network layer, these segments are now wrapped in packets with addition of IP headers. So layer 3 handles addressing on routing. Here IP protocol comes into picture and adds IP of source and destination. So your machine IP and the destination machine IP gets added here. So apart from data, source port, destination port, you have two more headers, which is source IP and destination IP. So your machine uses its local IP, say 192.168.1.100, and the destination IP is 93.184.216.34, the IP for the google.com. So your device checks the routing table, finds that the destination is outside your local subnet, and forwards that packet to the default gateway, which is the router or the layer 3 switches. Router protocols like BGP and OSPF make sure it finds the optimal path across the internet. So in transport, the function is the reliable delivery of the packets. The network's function is routing packets through the right channel. The protocol which deals in transport layer is TCP and UDP, while in network it's IP, BGP, OSPF, ICMP, IGMP, and etc. The PDU for transport is segmented, and for network it's packet. The device which is responsible for transport layer are the load balancer and firewalls, while the devices in network layer are the routers or the L3 switches. Now at layer 2, the packet becomes a frame. Here we are dealing with MAC addresses, unique hardware IDs which are added as an additional header. So this MAC address are the address of your desktop or laptop NIC, which is unique and no two devices can have same MAC addresses. The protocol we use here is ARP, STP, and PPP. The source MAC address is your laptop's NIC card, while the destination MAC is your router's NIC, which is responsible for routing that packet. So before sending an ARP request may be needed. Who has this IP? Tell me your MAC. Once it knows, the frame is sent out on the Ethernet line. Switches use layer 2 to forward the frame within the same network based on MAC tables and VLAN. Now the data link has two main functionality. One, MAC, which is media access control. So MAC controls how devices access the physical medium and places frames on it. And the second one is LLC, which is logical link control. So LLC provides error checking and flow control and ensures delivery is error free. So with this added header of MAC address, it goes out to the last layer, which is the physical layer. So finally at layer 1, the entire frame becomes bits, which are nothing but 0001s, and this goes as an electrical pulses, light signals, or radio waves depending on your connection. The frame travels as a signal from your NIC over a Cat6 cable, fiber link, or an Wi-Fi antenna. Bit timing, voltage level, connector standards all defined here. This is where physical faults or crosstalk can break your connection. The PDUs here is for data link it's frames, and for physical it's bits. The devices which are used in the data link are the switches and the NIC card, while the bits are the RJ45 or the cables which we use at the physical layer. As mentioned earlier, the function of data link is the error detection, while the function of physical layer is the raw bit transfer. So the reverse journey from server to client. The server receives the signals and the entire process reverses from layer 1 to layer 7, ultimately rendering the web page on your screen. So if any layer fails with a wrong IP route, which is in layer 3, block ports on layer 4, or invalid SSL in layer 6, the whole transaction fails. That's why this model is critical for diagnostic and security. So why tech team still uses OSI? Even though the internet uses TCP IP model, the OSI model remains a conceptual backbone. In TCP IP model, some of these 7 layers are merged. For example, the bottom 2 layers are merged as physical layer, while the top 3 layers are merged as an application layer. The transport and network remains the same. So in TCP IP, you have 4 layers as against 7 layers in OSI model. So I will explain TCP IP model in detail in a separate video, but this OSI model is widely used in troubleshooting. If there is no DNS response, check layer 7. If there is a packet drop, check layer 3. If there is high latency, check layer 4. If there is no signal, check layer 1. Security analysts use it to map attack vectors, while firewall engineers use it to set inspection points, and packet sniffer use it to isolate protocol level issues. So if you build or secure networks, you need to think in layers. The OSI model isn't just theory, it's your best troubleshooting tool and security guide. If this explanation has helped you, hit that like button, share with your team, and subscribe for more cybersecurity level tech content. Until then, stay secure, stay savvy.